Okay, class. So right now we're going to cover 4.1 related rates, and I'm going to go over first this first example that we have here in the book. So essentially, the example says air is being pumped into a spherical balloon so that its volume increases at a rate of 100 centimeters cubed per second. How fast is the radius of the balloon increasing when the diameter is 50 centimeters? So we're thinking air into a balloon, volume's increasing at a rate of 100 centimeters cubed per second. We want to know how fast is the radius of the balloon increasing when its diameter is 50 centimeters. So first thing I'm going to do is write down what my givens are. So essentially, for givens I have, so my given is dV dt. What dV dt is the rate of change for the volume with respect to time, and that is going to be 100 centimeters cubed per second. And then my unknown here, essentially what I'm trying to find is the change in the radius with respect to time. Okay? So that would be the rate right there, the related rates here, change in volume with respect to time, change in radius with respect to time. And there's no equal sign here, I apologize for that, but we're going to say when r equals 25 centimeters. And the reason I'm saying 25 centimeters is because obviously they tell us the radius is 50, so we take half of that. Now I need an equation that's going to help me to relate the volume to the rate, and I'm sorry, not the rate, the volume to the radius. And we do happen to know an equation for that. It has to do with the volume of a sphere, and a balloon is a spherical object. So we would say that the volume equals 4/3, this is a formula we should know, pi r cubed. Okay? Now with that being said, I'm going to differentiate both sides of the equation. The left side is going to be differentiated with respect to the volume. The right side is going to be differentiated with respect to the rate. And when we do that here, I'm going to have dV dt is going to equal 4 pi r squared dr dt. Okay? So now, in doing this, right, now what we need to do is manipulate things. So basically what I am looking for here is I'm looking for dr dt, right? And so what I can do is I can solve for dr dt. And when I solve for dr dt, what I get, and this is just a simple manipulation of the equation, I'm not even really finding the derivative here at all, I'm just manipulating it. And when I do that, I can say that dr dt is going to equal 1 over 4r squared times dV dt. Okay? And now at this point in the problem, all I'm simply doing is just plugging pieces that I know. I know what the rate is, and I know what the rate of the volume changes with respect to time, right? So now I can plug it in, and I can say dr dt is going to equal 1 over 4 pi times 25 squared times 100. Okay? And remember, it's centimeters per second, centimeters cubed per second here, right? Of that. So actually I don't even need to write that right there, because when we have the different rates, that'll cancel out. And so at this point right here, now I'm going to multiply, and when I multiply, 100 divided by 4 is 25. 25 is going to end up being in the numerator. I'm going to divide a 25 out, and what I really get here is dr dt is going to equal 25 pi. 1 over 25 pi, that is. And if I calculate this, I'm going to get 0.0127 centimeters per second. Related rate problem number 1. Okay, now this second example here that we're going to work on with respect to related rates is titled the sliding ladder problem, a pretty typical problem in related rates. So first we're going to explain it. So basically this line here that has a length of 10, and I'll go ahead and I'll put it in red so we can see that hopefully a little bit better here, but that this represents our ladder. Okay, so this is our ladder right here. And this ladder is leaned up against a wall, and then it's also touching the ground. And y represents the distance, right, from the ground to the top of the ladder, and x represents the distance from the wall to the bottom of the ladder. And so in this particular problem, we're just going to read it out, the example from the book. So it says a ladder 10 feet long rests against a vertical wall. If the bottom of the ladder slides away from the wall at a rate of 1 feet per second, how fast is the top of the ladder sliding down the wall when the bottom of the ladder is 6 feet from the wall? Okay, so first thing we want to do is we want to write what our givens are and what our unknowns are. So first, our first given here is our rate with respect to x. So we know they tell us how fast the bottom of the ladder is moving away from the wall, and it's telling us as it's sliding that the bottom of the ladder is moving at 1 feet per second, right? Now, what are our unknowns? So the big unknown here we want to figure out is how fast is the top of the ladder moving down the wall? What is the change in y with respect to the change in t when they're telling us that x equals 6 feet? So we could say that this is a known and this is a known here, similar to the previous problem that we had. So since when we're dealing with related rates, the big thing that we need to first discover is what is the relationship between the values here. And the relationship happens to be, since this is a wall, this is a right triangle, we can use the Pythagorean theorem, right? And using the Pythagorean theorem, I can say that x squared plus y squared is going to equal 10 squared, or 100. Now we're going to differentiate using the chain rule, just like we did in the previous problem. And when we differentiate using the chain rule, essentially what we're going to have here, remember when we put the 2 down, when we take the derivative, we put the 2 down in front and then subtract 1. So we're going to have 2x dx dt plus 2y. We're differentiating this with respect to y, so that's why it's dy dt, equals, and if I was to take the derivative of 100, the derivative of any constant is in fact 0. So now all this is going to take for us to do is just manipulate it just like we did the previous problem. So we're going to simply, and remember, what are we trying to solve for? You can't lose sight of that. We're solving for dy dt. So if we're solving for dy dt, I'm going to subtract 2x dx dt from both sides. And when I do that, I get 2y dy dt equals negative 2x dx dt. And now I'm going to divide both sides by 2y, and when I do that, I get dy dt equals negative 2x divided by 2y dx dt. And now I can simplify, and I get dy dt equals negative x over y dx dt. And I'm going to say it again, just like our previous problem. So there's a lot of repeated work here. We're going to go ahead and take what we know. What do we know? We know that x equals 6 feet, so I can go ahead and plug the x in here. We know that dx dt equals 1 feet per second, right? And so I can go ahead and plug that in here. The only thing that one might say we don't know is y, but guess what? We can solve it. And we can solve it by simply doing the Pythagorean theorem. Remember, just like up here, if I have x squared and I know that x is 6, so 6 squared plus y squared equals 100, I'm going to subtract 36 from both sides. I'm going to get y squared equals 64. All right, and when I do that, I'm going to get y equals 8. Now remember, I'm taking the positive square root because that would put think about it. If I got a negative value here, that would put me below ground level, which wouldn't make any sense. So now I'm going to plug in what I know. I'm going to plug in this, I'm going to plug in this, and I'm going to plug in this into my equation. So I get dy dt is going to equal negative 6 over 8 times 1. And when we simplify it, I get negative 3/4 feet per second. Okay, now example number 3 here has to do with filling a tank of water, and this tank happens to be the shape of an inverted circular cone with the base radius of 2 meters and height 4 meters. So the first thing we're going to do, and I always do in a case like this, is I'm going to go ahead and I'm going to sketch this cone here. Okay, and remember they tell us that the base radius is 2 meters, so the radius here, this would be 2 meters. And they're telling us that the height from here all the way to here is 4 meters. Okay, and they're saying if the water is being pumped into the tank at a rate of 2 meters cubed per minute, so that actually represents our given here. So our rate is going to be the change in volume with respect to time over the change in time. So dV dt is going to equal 2 meters cubed per minute. And then the unknown that they're asking us to figure out here is it says find the rate at which the water level is rising when the water is 3 meters deep. So the rate in which it's rising is going to be representative of h, so it's going to be the change in the height dh dt with respect to time when the height is 3 meters. So the relationship that kind of connects all of this all together here is a formula that we should remember from geometry, and that's the volume equals 1/3 pi r squared h. Now this is a great formula, it's very helpful. However, one of the things that makes it a little complicated is that I have two unknowns in here. I have r and h. So it would be great if I could represent the volume with respect to the height without r being involved here. And there's actually a really easy way to do that using similar triangles. So, what I'm going to do is I'm going to sketch what we're looking for, and basically the radius here would be unknown. The height here, would be unknown. But what we can say is we can say that r is to h. I'm going to put it over the side here. R is to h as 2 is to 4. Furthermore, I can say r is to h as 1 is to 2, right? Furthermore, I can say 2r equals h, and this is great, but what I'm looking to do is eliminate r. If I was to plug h in here, then I would, if I was to plug 2r in for h into this equation, I'd be eliminating h, and that's a huge part of this problem. So all I need to do is manipulate it one more time, and when I do that, I can say that r equals h over 2. Okay. So now as my next step, what I'm going to do here is I'm going to plug this value in here, and when I do that, I get the volume equals 1/3 pi times h over 2 squared times h. Okay. Now, in order to move forward in this problem, what I need to do is I definitely need to differentiate things here. And I'm going to need to differentiate, the left side obviously with respect to v, or the change in volume with respect to time, the right side the change in height with respect to time. But in order to do that, we're going to do some simplification first, and we're also going to do some rearranging as well. Okay. So let's first do some simplification here. So if I was to go ahead and simplify this whole thing, basically I would take h squared, so I'm going to have volume equals 1/3 pi h squared over 4 times h. When we simplify this, I'm going to get the volume equals 4 times 3, right, is 12 in the numerator, I'm going to have pi h